by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day. I want to welcome you onto the stream here today for our next lecture. Sorry, I'm getting really excited here today. So, if you're new here or you have not partaken in our fun here, my name is Dan. You can call me Dr. Page, you can call me Dan, call me Daniel. I'm a theoretical computer scientist. I'm here to teach you computer science here today. Well, in particular, I don't necessarily have to. I'm going to be conducting a lecture on that material. But what we're going to be doing is we're going to be exploring today a topic called regular expressions. Now, before I get into that, let me just get the chat open just in case. But just a couple quick things to note is if you want the availability to the notes and examples that I will be going through today and any additional ones I may mention or refer to, they'll be in these notes. You can find them on patreon.com/pagewizard. They are available at the supporter access tier and above, which is incredibly affordable for 1 month. It's quite wild. Some students pay hundreds of dollars for this stuff. I try to make it more affordable for people. So if you want to learn computer science affordably, if you want to support academics that work outside the universities to provide mission like this, consider supporting on patreon.com/pagewizard. If you like what you see so far, whether it be the production, whether you enjoy the fun so far, I haven't really done a whole lot right now, at least up to this point. Consider subscribing and telling your friends to come join the fun. If there's more people here, there's more engagement for the lecture, and naturally I consider the lecture as a byproduct of the audience and myself. So, because it's just not just me saying things, it's also this whole process of going through and deriving ideas together, and I consider that an important aspect of a lecture. So, other than that, I do have a survey that I'm looking about participants I just want like 5 or 10 minutes of your time just to, actually barely even, it'd probably take you about 2 or 3 minutes to fill out. Most people that I've talked to that have filled it out, they told me it just took them about 2 minutes to fill out. I just want to know about your availability, so consider filling out the questionnaire. You can check it on my social media, or just check it in the description whichever platform you're looking at this on. Please check it out. It gives me information to help refine the live schedule, because I think live programming is best when there's more people available, and I know some people like watching these when it isn't live, and I want to make it sure that I can make the live content available for those that maybe can't necessarily participate. So, that being said, a couple of quick remarks. Note that if you have a question or anything of that sort, just put it in the chat. Feel free to put anything fun in the chat. Come and join, have discussion. If you want to make a joke, go for it. Like, the chat is there. Keep in mind that I do hear the chat, and I also can visibly see it. It's in a monitor just over here. So if you ever see my eyes go this general direction, because there's a monitor right there. I should also note that whenever the chat is on the screen, usually I put it up in between or at intermission points during the lecture. So this is normally a time where I'm transitioning to a next topic. Normally this is a good time for me to talk more about more sophisticated questions, or if you want to recap on a couple things that I've discussed. So do note that when the chat is visible on the screen, the text-to-speech for Twitch, for instance, is audible. But if you do not, if it isn't visible on the screen, you won't hear it, but I will still hear it. So just please keep that in mind. So, Other than that, we're going to be exploring more theory of computation today. So I must stress that the topic we're going to be discussing today and possibly next week, these are topics that are heavily practical too. So I'll be talking about the theoretical aspects of these topics, namely to give you an introductory insight into how it works and how you can understand the key concepts. I must stress there's a giant rabbit hole you can go down with many of the topics we discuss here in our Theory of Computation series. So in this case, I will mention that regular expressions are these they're all over the place. So don't think of this just as some fun little exercise. It can be, most certainly, from an academic standpoint. It could be just thought as a fun exercise. But most certainly it does have a fundamental relationship with many of the things we've talked about at this point. Sorry, I'm just losing here. I'm getting really excited. Let's get into things. You get the point I'm getting at. There's many things out there, and I must stress the things we're going to talk about here will help guide you in understanding the main ideas around so-called regular expressions. So once you have those fundamentals, it's much easier to go pick it up if you're curious about this concept, which also can be used in many applications. So that's just as true for many of the things I talk about here in the Theory of Computation series. Most of the things I discuss here have some type of application. And that's not very surprising given the fundamental nature of many of the topics we're discussing here. So for example, finite automata, these are not just esoteric topics that are archaic. These are things that appear in all sorts of different forms in computation. Hence why it's a backbone for such applications. So let's get into this here today. So today we're going to be talking about what regular expressions are. So before I get into that, I really want to motivate where we're going with this. I must stress that this is a wide topic, many applications in relation to this concept or this family of concepts. But I'm just going to be talking about what a regular expression is, and I want to layer it into the discussion we've had up to this point about regular languages. So as the name suggests, there's going to be some relationship with a couple of different things here. But I'm not going to get too deep on that, but I will give you the main inclination that regular is there for a very good reason. And we've already heard about regular operators, and we've also heard of regular languages before. So let me frame this appropriately. So when we describe or recognize. Now, note when I say describe, I also could mean define as well. Or recognize a language. We very often would describe it up to this point as, indeed, a formal language. But how did we recognize these languages? How could we describe a language? What if I told you it was a regular language? Depending on how we defined the regular languages previously, what would you say? Well, that means that there exists a deterministic finite automaton such that it recognizes said language. That's what we gave as our initial definition of a regular language. So there's these, what I would describe are machine-like descriptions. So we have this machine-like descriptions. So we could describe a language using a machine, right? So what are some that we've seen up to this point, just as an example? Well, I just mentioned the deterministic finite automata. So we can use DFAs to do this. We also talked about how NFAs were also going to do this. We also talked about epsilon NFAs as well. So all of these provide machine-like descriptions of languages. So if I wanted to say, come up with a way of recognizing a string in a given language, I can design a machine, and that machine, presumably if it's correct, can recognize said language, meaning that if it accepts, that means that that string, the input string, belongs to that language. If it rejects, then it does not belong to that language. And the language of the machine is a formal language. So Naturally, now, when you think about this, this is one way I could describe languages. Let's go back a few steps back. When I defined a language, what was a language? It was a set of strings, right? It was just a set of strings. And we also had this discussion about regular operators, right? Do you recall I talked about we talked about these things called regular operators, right? Remember we talked about these? There were some examples of operations I showed you. For example, we talked about union, we talked about concatenation, we also talked about star. Those are examples of regular operators. These are the main ones. These are what we would call regular operators. We've talked about these, but what did we apply these to? Well, we could apply these to languages, right? So if I give you a set of strings, I can apply these operations. And what did I tell you previously? Now, I didn't prove it, but what did I tell you? Is that when you perform on two languages that are namely regular, if you give you two regular languages, if I perform any one of these three operations, what happens? What kind of language do I end up with? A regular language. Now, I'm not going to go into detail about the proofs for those because at this stage, I don't quite have the machinery for it, or if I do, actually I do have the machinery, I have those guys over there, but I haven't gone to those details quite yet, okay? Because I haven't really established too many things at this stage about regular expressions. Namely, we know that we can describe a language, we can perform these regular operators on said languages. What if there was a simpler way for me to describe a language based on these regular operators and being able to represent languages as variables? So this is where I want to go with this. So instead of it being like a machine-like description, suppose that instead we were looking for, coming back to our formal languages, suppose we had an algebra, I'll use this comparison, an algebraic or declarative description. I'll say an algebraic or declarative definition. So meaning that just like in algebra, at least the algebra you're probably used to, where you have variables and you can describe operators within that algebra, you can have it so it applies it to numbers and it evaluates expressions, right? That's something that you're familiar with from, say, we're talking about like school grade algebra. So this is what regular languages are going to fall under. But here's the neat kicker. We can actually describe these languages using so-called regular expressions. So the analogy I want you to think about with this is, imagine you have like an algebra that you can describe sets of strings with. So regular languages with other regular languages. And as I mentioned, there's closure properties on all three of these, for example. What if I could describe to you a language, so which strings will get accepted, using an algebraic or declarative definition akin to algebra to variables and numbers? So that's what we're going to be going for with regular expressions. So let's define what a regular expression is. So you'll notice that I'm not going to be talking about machines, at least at this stage. I'm not talking about machines. Instead, what's going to happen is I'm going to give you a declarative way of talking about a language. So you can imagine, I want to describe a language to you. I can use one of these expressions. I haven't proven to you that this, in fact, will be a regular language, but I'm just trusting that you will follow along with me at this stage. So suppose that I want to have some way of describing a regular language to you, but doing it in a way that looks a lot more like algebra for someone like perhaps yourself. So we're going to define it inductively. So there's going to be a basis, and an inductive component. So there's going to be 3 cases in the bases. So these are kind of like your building blocks for a regular expression. So I'll give you the first 2 cases. So the first case and the second case, I'm just lumping them together because it's a little less space for us. So the first thing you need to know is I can describe as regular expressions the empty string epsilon and the empty set or empty language. These are defined as regular expressions. These are regular expressions. And these namely represent, so representing the languages, they represent the language that consists of only the empty string and the empty language, respectively. So to be a bit more precise about what I'm referring to, so if I ask what the language, so you can take one of these regular expressions and ask what language it represents. So I'm going to use notation similar to what we use for the DFAs, NFAs, and epsilon NFAs. So the language of, say, the regular expression that represents the empty string, like this is this set of strings, namely just 1 in there, the empty string, and the language of the regular expression that represents just the empty set or empty language is empty as well. So notice that I'm using epsilon and the empty set here. I'm using both of them as symbols for regular expressions. So please take note of that, is that these are expressions. So these are regular expressions in themselves. So it's just one symbol. But they're each have their own special labels, okay? So empty string, that is actually the set containing the empty string, and empty set is just the empty set or empty language. So just as a note, actually no, let me give you the third one here. Naturally, I would like to have it where I can have just a set with just a symbol in it as well. If A is any symbol, so imagine you have a symbol that you would like to express, then, now to make this a little easier for us to parse, I'm going to typically use a boldface version of the symbol to represent that regular expression for the symbol. But because I don't boldface my characters on the board, I'm going to underline them instead. Then A is a regular expression. So just to be clear, this underlined version refers to the regular expression of the symbol A. So this is the regular expression of A. So do note in this case that the language of the regular expression for symbol A is just simply the set that contains A. That's it. That's it. So these are actually all of our cases in the bases. I must make an important remark though, because we can build more sophisticated regular expressions by introducing variables. So note that a variable such as say, a capital L, or this could be, usually it's written as a capital letter. So it says typically capitalized. It could be like a capital A, it could be a D, it could be whatever symbol you like, as long as it's a capital letter. It makes it a little easier to distinguish from symbols, because normally you use lowercase letters for symbols, usually. But whatever this is going to represent a variable. Can be used to represent a regular language, which we'll use this in our inductive cases. So if ever you have a regular expression, we can replace the entire expression with a variable, because remember, it represents a regular language. Hence, if I give you a regular expression which has a language, right, I'm just going to take that and I could represent that as a variable. So let's now proceed to the inductive case. Sorry. So now, as I mentioned about these regular operators, so there's our regular operators over there. Those are going to characterize the case inductively, because as I told you, when I take two regular languages and I apply a regular operator on them, I still end up with a regular language, right? So they're naturally going to be a part of this part of the definition, with an extra case. Just more of a technicality, though. We introduce regular operators. So we're going to have a case for each one of the regular operators. Plus, we're going to introduce parentheses, so we're allowing parentheses as well. Just like you'd be familiar with when you're playing around in algebra, right? So you have your like multiplication, addition, and you have like parentheses, you may have exponents and things like that. We didn't have the same kind of thing in play here. We're going to have an order of operations, and we're also going to have precedence around these parentheses. So I'll get into more details about that in a moment. So for each one of the regular operators, I'm going to define a case. So first we have union. So if I give you, suppose that I give you two regular languages. So suppose E and F are regular, like they could be regular, well, we'll call them, we'll go regular expressions. So suppose that E and F are regular expressions. Remember, it's just a variable that denotes a regular expression, which in itself has its own regular language. So suppose E and F are regular expressions. Then the union of E and F, which will be noted with this plus sign as a regular expression. So I'm just using this symbol for us here. Depending on where you're running into regular expressions, they may use a somewhat different symbol. But the point is in our discussions, we'll use this plus sign for union. Previously, we had seen it for specifically sets. This is for regular expressions. So this is a regular expression. So if I take the union of two regular expressions, so I apply a union operation. So this is a regular expression, that's a regular expression. I perform union operation. Whatever the result is still a regular expression. So where E, and I'll just refer to it as plus sometimes as an abbreviation. So where E plus F denotes the union of the language of E. So remember, E is a regular expression, and the language of F. I.e., and now I'll pull out the regular expression connection with the regular operators. i.e. the language of E plus F. So this is the resulting of our regular expression where I apply the union. This should be the language of E union the language of F, as per in our discussion for regular operators. Seems pretty straightforward, right? Because this is just us giving a special name, namely the union operator, for our regular expressions. So remember, all it is just a way of describing what happens in a specific, so it's giving us a specification of the language. When I could describe it like this, so suppose I had a regular expression for E, regular expression for F. If I add this plus in between the two like this, that specifies a language. It will be this language. But this is the regular expression. So next, we got concatenation. So this will feel a lot like I'm just revisiting regular operators. So EF, so I'm just not going to, sometimes you might write a dot in here explicitly, or just like literally a dot like this, but I'm just going to write them right beside each other like this. Is a regular expression where EF denotes the concatenation of the language of the expression E and the language of expression F. To be a bit more specific, the language of the concatenation of E and F is equal to the concatenation of the language of E and the language of F. So I put the dot in there just to be a little bit more specific with you, because I used that notation along when I was defining regular operators. So note that I would normally write those right beside each other as well. Like, that's perfectly valid as well, just as long as it's clear for the reader. So I'll just make a remark as I noted it previously. So if ever you need like a specific operator, very often they explicitly say and write this as a regular expression, often it's using a dot. Usually you just write dot, like a period, as opposed to a center dot like that. So often a period is used to denote concatenation. So what I'm saying is if it's unclear what that means, just write E dot F where this is just a period. Wherever unclear. So there's case number 2. Next, I have to talk about the star operator. So let's talk about the star operator next. The star. So naturally, if I give you a regular expression, if I apply the star operator to it, so I'm just going to write a star like this. This is a regular expression denoting the star or closure, wherever terminology you would like to use, the star or closure of the language of E. To be a bit more specific, the language of E star is the exact same as me saying, if I give you the language of E, so suppose it's the same, so suppose I give you the language of E, I take this and I apply the star operator as per our regular operators. That's what this is. Now next, I have to talk about parentheses because I promised you I was going to talk about those. So, how do they work? So, it's going to be a fairly simple rule, but it's a versatile one. So, what do you do with parentheses? So what happens with parentheses? So if I give you a regular expression, I put parentheses around it. So suppose I parenthesized the expression E. This is also a regular expression. This is also a regular expression. I notice the language of F is a little off. Let me just... That should be a bit better. So, anyways, so is also a regular expression. That says expression. It's sort of melting over there. And is the same language. It's the same language as E. I.e., suppose I ask you what the language of the parenthesized version of E is. Well, this is just the exact same as the language of E. So notice that it's just the exact same if I put the parentheses around it or if I didn't. But sometimes it's helpful to have those parentheses to help me denote or carefully specify which things are being applied to a regular operator versus which things are not. So that order of operations with the regular operators is much clearer. So let's talk a little bit about that now. So this is the definition of a regular expression. So I'm just going to make a remark about how order of operations generally works. Okay, so just big note. So this is a big note. So this will save you a lot of time. Okay, it's a little unclear how these different operators work if you're not familiar with the regular operators. So order of operations or precedence. For regular operators. For the regular operators is as follows. So star comes, so we got star first, then you got concatenation, then you got union. Or equivalently of star, concatenation, union. If you want to talk about them as languages. So that's for regular expressions, this is for regular languages. So this is kind of like the language world, this is the expressions world. So let me give you an example, what I'm referring to. So suppose I give you this regular expression. So I have 1, 0. So I'm going to have 1, 0. Suppose I define this over the binary alphabet. So suppose I have 1, 0. So I have each one of these symbols. I have concatenated. I have done some sort of concatenation here. Then I'm going to have a union operation somewhere, and then I'm going to have this, this 0. Now, you might be staring at this and asking, Dan, what does that mean? It's because it's a little unclear if you're not familiar with what this should be doing. So you see there's a star operator. What is it associated with? Well, let me clarify this. So this is how you would group this. So remember, star comes first. So I'm going to use parentheses to help clarify any confusion about how this is actually grouped together appropriately. So first you see a star operator over there, right? I told you that comes first. So you do that first. But notice that it is only grouped with the 0. It is not with the 1, right? So we have 0 star, right? So the 0 is associated with the star. Next, what else did we say? We said, so now we've taken care of the star. Oh, how about the concatenation? Okay, concatenation is next. So notice that the 1 is right beside the 0, star, right? And then we have the union operation. With what? The 0, right? So the expression for 0. So this is actually how, when you get used to regular expressions, this is how you might interpret this. So notice that the 0 is only grouped, like the star is only associated with the 0. It's not with 1, 0. And take note that you wouldn't apply the union operation until you've carried out that concatenation over there with the result of the star operation. So please take note of this for the grouping. And I thought I would do one example just to illustrate how you can express a language with this definition. So let's do an example. So we'll do some more examples of designing regular expressions, but I thought I would keep something nice and simple for our discussion here. So suppose, because you'll get a little bit of a feel for this. Suppose I wanted to have a regular expression that's supposed to represent all binary strings. Now, you may not have thought about this, but all binary, like a language that consists of all binary strings, that is technically a regular language. You can design a deterministic finite automaton that can recognize that, right? I'll leave that to you as an exercise. But I want to take advantage of some things you know about how these regular operators work to help build a regular expression that can that describes. So notice that instead of talking about accepting or rejecting, I'm going to talk about describing. And if the string in question is in fact one that matches the specifications of the regular expression. So in this context, I'll be describing, I'm giving you a descriptive way of characterizing all strings that, if it fits the form of the regular expression, is indeed been recognized, right? So you can imagine, like in practice, if somebody like designed one of these things on a computer and then said, okay, this is my regular expression, and I give you a string, I would like to know if it fits the form of the regular expression. Now, I'm not going to go into too many details about how or exactly that works in this lecture, but most certainly, like I said, it's a declarative way of talking about a regular language. So if I give you a target string and I would like to know if it is of that form, so you can imagine I'm trying to detect if it has that form or if it has a certain key phrase in it or something like that. There's many, many applications for these regular expressions. But I just want to describe a regular expression for all binary strings. So remember, it's a descriptive way of talking about regular languages as opposed to our machine-like descriptions we've had previously. We're not going to be talking about accepting and rejecting. We're going to be talking about just simply, if I give you a string, is it one of these of the regular expression? Okay, because remember, all the strings that get accepted will have this form. So please note. So I want to kind of start off simple before actually we get too far. So let's go through this carefully. So if I had all the binary strings, what would that look like as a regular language? So suppose I give you a language. It consists of just 0 and 1, right? So I want to walk you through step by step how we can come up with a language that would be all binary strings. How did I normally describe that to you? Well, I can have a 0 or a 1, right? Binary strings can look like this. It could be the empty string, right? It could be 0, it could be 1, it could be 0, 0, it could be 0, 1, it could be 1, 0, it could be 1, 1. You could keep doing this, right? Well, I have a 0 or a 1. What did I use to describe all binary strings previously? I'd apply a star operator to this. So let's walk through the process of how I would construct this resulting language. So how did I do it? Well, it's 0, right? There's a regular expression for 0, right? There's another regular expression for 1. Now, if I want to put 0 or 1, as I have in this set, right? You pick one of them. Or possibly none, right? But the thing is, I have to pick, I get to pick, right? So suppose I want to pick a 0 or 1. What would I do here? So please notice that the expression 0, so I have the regular expression for 0, because I have one symbol here, 0, and I have another symbol, 1. I'm going to take a union operation, right? Because remember, what are these? This is the language that consists of the symbol 0. This is the language that consists of the symbol 1, right? If I wanted to have 0, 1, just 0, 1 without the star, I would want to do a union operation to them. But this is the description of that, right? This is a regular expression for that. So this right here, what I've just written here, is the language. So if I ask what the language of this expression is, it is the language. Is the language 0, 1, where these are our symbols. So what did we do next? Like what was the next step in this process? We applied the star operator, right? So naturally, I want to apply the star operator, but I need to do it carefully. I need to use parentheses to help me do this. So applying the star operator to this expression, we get what? Well, how would I apply the star operator? Well, I want it to be such that it is encompassing all. So I want it to be just this set here, and I want to apply star, like I have here. So we know that just this set without the star is, in fact, this represented by this regular expression. So all I do is I take that regular expression, group that all together, and I apply the star operator, which is going to be representing the following language. So which is the language of this expression is in fact the desired language, a set of all binary strings. So now if I give you any finite alphabet, so any alphabet, can you see how you can describe like if I write down like sigma. So we normally use this as some finite set, right? Do you see how sigma star would also be a regular language? Just to motivate this, I'll do another example just to illustrate the point. Because remember, if sigma is 0, 1 like this, it's exactly what I wrote here, right? So if I wanted to have sigma star like this, I can generalize this even further. Like suppose I gave you another set for the alphabet, A, B, C. How would I describe the set of all strings composed of the symbols here? Well, I would have a regular expression for each one of these, right? And I'd perform union operations among all of them, right? Because I want it to be able that you can pick any one of them, but do it 0 or more times, right? So sometimes when people talk about regular expressions, they sometimes will allow you to use the alphabet as a symbol. So very often this is used as a shorthand for something like, so if I, instead of writing out, say, this like this, they may write just this. So that's just one example. I thought that would start off with something nice and easy for us. But we're going to be seeing some more examples of regular expressions and designing them. But yeah, so are there any questions? Any questions at all? So while I'm getting the next part here prepared, I thought I would give you a little bit of commentary on regular expressions and how they get often used. So I did make a little blurb about this in my notes. So for dramatic purposes, I'll highlight a couple of things that I have in here. So very often they're used naturally for compilers. But also they're used for searching. So suppose you have a really big set of text, like a really, really big set of text. And I want to detect in there certain patterns. So certain applications like this, I think in Unix-based systems, I think they use grep. I think grep is one example. In fact, you might see that it has some similarities in there, I believe as well. AWK also does use such a tool. But you must stress that regular expressions provide a user-friendly way, providing they know what a regular operator is, to describe what a format for a string or a pattern for a string. So suppose that I give you a big body of text and I would like to know if there is a certain pattern in the string, or I want to detect a certain part in the string. I want to validate a part of the string. You can use regular expressions to do this. So if you might ask how this works. So let me give you an idea of how this works. So somebody gives you a regular expression. So the reason why I'm doing this during the intermission is because I haven't yet given you the mathematical machinery to convince you of this yet. But here's sort of the process you can think of. So you can imagine you have your system. So imagine you have the system. So you have a program, it has regular expression. So you have some system somebody's designed. So what it does is you give it a regular expression, which some people abbreviate as regex or regex, regular expression. So you give it to the system. So this is some program. And what it will do, it will construct and convert this over to being a DFA or NFA, which we've already talked about those. And what it does is it will simulate to complete the search. That's very often how regular expressions are actually implemented, is you give the regular expression. So this is a user-friendly way of describing the pattern or format for validation of a string. So very often when somebody gives you like a body of text and you want to say, hey, look, like I'll give you one basic example. Because a lot of text-to-speech programs actually use regular expressions. In fact, I could, for example, with our text-to-speech program we use, we could incorporate regular expressions into it. I haven't. I've only put some basic filters in. But suppose I want to put some filters into my text-to-speech program such that it puts out certain words. So if a certain nasty word, say what some people call the fun words, if some people wants to put one of these fun words into the chat, and I want the text-to-speech to not say the word, instead it says a different word. I would like it to detect within the body of the text of the chat. So if somebody puts a message out there, the program takes that message and it looks for that message. Now, you might ask how it looks for it. It might do something like this process. I don't know exactly what that program uses, but most certainly this is a common process. So instead of it being where, oh yeah, it just has this thing, what it will do is you describe a regular expression. So on my end, the user, I would describe the regular expression. So say if I was a programmer or the user, I would like to detect certain pattern, like say one of these nasty words. Like say, I have Miss Kitty here, who's just showing up to interrupt the stream. Yeah, you. We're talking about you. Suppose somebody puts Miss Kitty in the chat, and instead I want to put Nasty Kitty in so the text-to-speech says Nasty Kitty instead of Miss Kitty. I could design a regular expression that looks for Miss Kitty in the chat. Maybe I might want to look for it where it optionally allows for periods or not periods. What I could do is design the regular expression as the user or programmer, and then what happens is it gets converted over to being a DFA or NFA, which the program underlying that's being used to support the regular expressions can tell me where it's happening in the string or if it exists. So for us, I'm not going to be worrying so much about that at this level. We just want to know about regular expressions and what they do and how to design them. But the point I'm getting at is that you can use them in all sorts of different settings, including in searching for large bodies of text. So this is something that you might use if you have a very complicated form for a desired target string. So if you're looking for certain key phrases, you can design those into a regular expression, as we're going to see in some of our examples. Then what happens is you're specifying or describing the language of strings that would be accepted or rejected by the DFA or NFA. That's one way you could think about it. But remember, you think of the regular expression as the form of the language. So just think of it as all strings that would be accepted by the language. So any one that fits the form would be a part of that language, just like you would talk about for membership of that language. So it's not that it accepts or rejects. That's not how this works. That is a machine way of describing the language. We're giving a systematic way, but not necessarily machine-like. So it's not machine-like, it's declarative. Just like when you talk about in a programming language, you might talk about variables and I assign values to those variables. I would like to have some way of describing, so if I give you some string, does it fit that form or it doesn't. So it's a language, it's very much a language-oriented declarative way, just like when we talk about an expression, say in algebra. But you can perform operations on it, you can do all sorts of other things with it. But yeah, so I thought I would give that fun example. So say if you're watching this on Twitch and you're like, hey, look, how can I use regular expressions? There's a lot of text-to-speech programs, including such as the one I'm using for this stream, that do use regular expressions. So you can, as the user, you can describe regular expressions, and you can use these to determine if there's a naughty word or a word you don't want to see in the chat, like Miss Kitty. I didn't do that here. It would have been actually really funny to put that into here to see what would happen, just to illustrate my point. But you can give many, many patterns like this, and you can design the regular expression to look for all of them. Now, the reason why I mention this is much more for sophisticated patterns, because there's a trade-off, because naturally when you go through a process where you're building one of these machines, right? Like if you had to build one of these machines, it better be worth it, right? You're not just looking if the symbol A is present in the string. That's as simple as just going through with a loop if we're talking about it as a very practical thing. But this is a very arbitrary process you can go through. Like it's very generalized. So in practice, you might consider or may not consider using a regular expression. But if you have a much more complicated form, that requires a little bit more than just simply passing through the string once to check for something. It might require several operations to be done on the string. This might be something you would consider in practice using. So let me just erase the board here. Are there any questions or any comments about our fun application that I had mentioned here? So yeah, so text parsing. Parsing, it's your best friend. A lot of people will tell you, hey, look, if you're interested in parsing big bodies of text, you may want to know a little bit about regular expressions. Searching in big bodies of text, finding patterns. If they're a little trickier than just detecting if one letter is present. In practice, you may consider using a regular expression to describe your target string. And naturally, they can be described quite nicely with regular expressions. So a lot of programs actually do support regular expressions. They're a fundamental application. Well, I wouldn't say an application. They're a fundamental concept in formal language theory. There's something like, I mentioned this name before. I mentioned Claney before. That name's going to come up later this lecture, but I just wanted to mention that like a lot of what he did around like regular operators and stuff is closely related to this. Like it's basically, if there's something I could point to, is like, oh, this is Stephen Cole Claney's thing. Like this is one of the big things. Okay, just to give some context. So there aren't any questions. I dumped quite a bit of information on you while I was just erasing on the board here. But just please note that you can use regular expressions in all sorts of different applications, such as searching. They're used in compilers very often if you're trying to determine parts of text. They're very often used. They're used in lex analysis as well. So if you ever heard of something called a lexer, these sometimes pop up as well. The point I'm getting at is if you're curious about compilers, this is just another piece to the big puzzle of compiler design. Likewise, they're used lots in text search. So if you're interested in searching, like say if you're, and you may actually run into these quite a bit with web browsers. So web browsers, obviously, many times you're looking for a specific form in a target string. Regular expressions pop up there as well. But yeah, no, hopefully you thought that was interesting. So it's not just that we're describing these just strange algebraic rules that you may be unfamiliar with. They actually do have some purpose that is much more beyond the scope of this lecture. Okay. Let me know in the chat how you doing, by the way. So previously we had designed, I'm getting really excited here. So previously we had defined what a regular expression is. So remember that this is a nice declarative way of describing a regular language. I haven't got too many details about why it's a regular language, but most certainly I'm hoping that you'll cling on tightly as I keep using the word regular over and over again. It will eventually get to the point where we can actually talk about that much more intimately. So, I thought we would talk about designing regular expressions. Ooh, this marker's looking a little bit funny. You know what that means? Boo! It's gone. It's gone. Let's get a different marker. So, we're going to be designing some regular expressions. So we've seen a basic example before. We've seen actually how we can describe all of the binary strings. So I thought we would start off with something I would argue is not super easy, but something you maybe are not as familiar with. It's going good. No, we're going to be talking about regular expressions. So I just defined what regular expression is, and we're going to try designing these things. So we're going to go through some examples of designing regular expressions. So I thought, or for our first example, I thought a good idea, imagine I wanted to describe to you all strings that alternate on ones and zeros. So suppose I want to have a regular expression that describes all binary strings. So those are those that consist of ones and zeros. So I want ones that alternate on ones and zeros. So 0 or more of these symbols. So 0 or more alternating ones and zeros. So just to give you some examples. So what this regular expression should describe are strings that include this. So 1, 0, 1, 0, right? They alternate on ones and zeros. So likewise, 0, 1, 0, 1, right? They're alternating. That's the point I'm getting at. So notice that these two strings, they have to be a part of the language that represents the regular language we would like to describe. So that's our goal, is we're going to try to come up with a regular expression that's able to, if I gave you this string, this regular expression describes this string. Likewise, some other ones. So like 0, 1, 0. Notice that in this case, it ends with a 0 and starts with a 0. Notice it's a little different than those two. So naturally, I would also like to include this one as well. So notice that all of these alternate on 1s and 0s, right? Do you see that? So how about let's consider a few other strings. Would this string be a part of, like if I come up with this regular expression or language, its corresponding language, would this string be a part of that language? Is that a part of the language? So if I'm coming up with this, would 111 be one of them? How about this one? How about 110? Would these two be a part of the language? Are they alternating on 1 and 0? These ones wouldn't, right? Because they're not alternating. They're not alternating. See, these two would not. I don't want these ones to be described by the regular expression. Only those 4, for example, and many more. There's infinitely many of them. So notice that I can keep going on like this, right? I could go 1, 0, 1, 0, 1 like this, and so on. The point is I would like to design the regular expression such that it's just alternating 1s and 0s. So any of these 5 that I have here should all be things I can describe with this regular expression. Namely, these are all strings in that language. But these last two, no, these aren't a part of that language. So I'm going to show you a couple different approaches for me to come up with a regular expression for the language in question. So the first approach, if you're dealing with a really tricky case, the first thing you might try doing is just exhausting this. Question. 1, 0, 1, 0, 1, 1. No, that wouldn't be a part of the language. So if I added a 1 here, it wouldn't be because it's not, it would be a 0 that would come after the 1. That's a good question. Excellent question. Yeah, so what we're going to just have it is so it just alternates on 1 or 0. So it's 1, 1, 0, 1, 0, 1, 0, or 0, 1, 0, 1, 0, 1, up to, it's 0 or more symbols of that. Excellent question. So the first approach I was going to suggest is that we just try breaking this into cases. So sometimes when people come up with regular expression, sometimes it's a little bit, it's a little tricky because it may have several cases. Do you notice that the 4 here that I gave you, notice that they actually can be broken into 4 cases. So each one of the cases actually is represented by one of these examples. So sometimes when you're coming up with these, you might think about, okay, what kind of strings, what's the form of the string? So when they get a little complicated, just break it into cases. And a natural idea here is that if I can describe the strings for one case and for another case and for another case, what can I do with each one of those? Well, if I design a regular expression for one case, and I design a regular expression for another case, and I design a regular expression for another case, so say 3 cases. In this case, we're going to have 4 of them, I believe. What can I do with that? There's something really neat about it. Well, I'll let you think about it. What we're going to do is we're going to exhaust all ways we can write alternating 1s and 0s. So here's one possibility. So I'm going to start off with the easiest thing I can possibly try doing. Do you notice that in this first case, all it is 1, 0, 1, 0, and it keeps going, right? I can have 1, 0, 1, 0, 1, 0, right? Do you notice that every time I write down 1, 0 like this, and I write another 1, 0, then I write another 1, 0, notice that the string always starts with a 1, ends with a 0. So I'm going to consider this case first. So we're going to first consider the string string 1, 0. So notice it's just the symbols 1 and then a 0. It's not 10, just to be very clear. So how can I describe this just as is? So suppose I wanted to have a language that is just going to be consisting of only one string. It's going to have two symbols. It's going to be 1, then a 0. So I think that maybe might be a good place for us to start. It's so that we can have it so it has two symbols in there together as one string in one language like this. So if we can do that, notice that if I just put a star on this, I can repeat this 0 or more times, right? Notice that if I had it where I pick it once, it's just 1, 0. If I pick it twice, I get 1, 0, 1, 0. If I pick it 3 times, I get 1, 0, 1, 0, 1, 0. So if I get that, we've covered what looks like this first one here. So let's try to figure out how we can cook this up. If I could cook this up, there's our first case. That would cover this one here. So I must stress that we're just doing all alternating strings like this. It doesn't have to just be only those 4. It could be any strings that have this form. These are just 4, think of it like test cases. So here we go. So how can we come up with a regular expression that corresponds to this? Let's think about it. So the first thing is that, how do I get first this in here? Well, I can take one, I can concatenate that language with this language, right? The one that consists of symbol 0, and then so I have these two languages. I concatenate them, and I take each one of the strings in here, concatenate it with each string in here. So if I wanted just this without the star, I might use a concatenation. So if I concatenate those two, piece of cake, right? But what is that as a regular expression? So we can obtain this by concatenating the expressions. And what are those expressions? Notice that there's a regular expression for this, right? It's just one bold, but I underline it because it makes it a little easier for you to determine from the symbol 1 versus the expression 1, as we discussed previously. And this is that, right? So if I concatenate the two, the result of that should give me this without the star, right? By concatenating the expressions 1 and 0. So, i.e., if I represent this as a language, what I'm saying is take 1, concatenate the language that consists of this one string, which is one symbol, 1. I concatenate this with the language that only consists of one string, namely this string that's just a 0, that gives me 1, 0. So what this would look like as a regular expression, you might write this as 1 dot 0 like this. Or you'll find very often I'll just write it without the dot. Whenever it's unclear, I just simply will just write it without the dot because they're right beside each other. But if you're typing this into a system that was taking in a regular expression, it often will use concatenation maybe as a dot, whatever symbol it might be. It's a good idea to specify what the operator is. But for us, since we're doing this more abstractly, I won't write it all the time. Whenever it's unclear, I will, though. Okay, so now, so far we got that. So now all I have to do is one other thing. Need to get 0 or more occurrences of 1, 0, right? So what's the operator I should use? What's the operator? I'm going to use a star operator. So now, I need to do it to all of the expression, right? So this would represent this right here. So you might ask, Dan, what is this? What's the language of this? This consists of all binary strings that consist of nothing, right? You can take nothing out of this, right? You can take, so you have nothing. You pick it once. You pick it twice like this. You pick it 3 times, and so on. That's what this regular expression actually represents. So that's actually the language of this regular expression. Yes, exactly. So this is the first case I was thinking about. Now, you can think about this in many other ways, but this is the first case I was thinking might be ideal. Because notice that the way the string begins and ends can actually change from just this first one, as I mentioned. Notice that this first one here, so this would account, for example, see, notice it's right here, right? So far I got that one accounted for at least. Think of these like our test cases. So notice that this one starts with a 1, ends with a 0. So maybe it might be natural to consider when it begins with a 0 and ends with a 1. Then there might be another case for when it starts with a 0, ends with a 0, and then maybe where it has a 1 and ends with a 1. So you'll notice that the first case is going to be very similar to my second case. So let's consider, so to get all strings, that start with 0 and end with 1, I was going to suggest that we simply reverse the way the concatenation occurs, right? Right? That's all we need to do. So to note that, remember, if I want 1, 0, 1, 0, 1, 0, if I want 0, 1, 0, 1, 0, 1, what I'm suggesting is we just swap these two around. So just take 0 and 1, make it 0 first, then 1, instead of it being 1, then 0. i.e., we will have 0, 1, star, where the 0 and 1 are together upon a concatenation there. So this is the expression for the symbol 0, this is the expression for the symbol 1. I group them together with parentheses and I apply the star operator. So notice now this will definitely include strings such as this one. But now we have 2 more cases. Exactly. Very good. So let's head over here. Let's take on the 2 remaining cases, because this definitely won't cover all of them. Because somebody could potentially, just as a quick example, somebody might want to just give you a 1, or they might want to just give you a 0, for example. Or it could be the case like we have these 2 strings here. So I need to make sure I account for those. If we don't account for them, oh boy, I'm missing some. So here we go. So naturally, the next case is when we start with a 0, end with a 0. So please think about how we might use some of the ideas we have so far. So remember that up to this point, we've seen how we can start the string with a 1 and end with a 0. And we've also seen how we could start the string with a 0 and end with a 1. So all we need to do now is incorporate both of these corresponding ideas we had over here with the idea that we start with a 0 or start with a 1, right? In each of those respective cases. So notice that they're going to be very similar to what we had before. Yeah, you're right on the money about what I'm thinking about. And there's many ways that we can actually represent this. I'll show you a different way of going about it. So check this out. So to obtain all strings that start with 0 and end with 0. So I'm just going to simply adopt the first idea we had. Do you notice that in the first idea that we had, we started with a 1, then we ended with a 0, right? So all I'm going to do is I'm just going to concatenate whatever the result that was. I'm going to put a 0 on the front. So I'm going to take 0 and I'm going to concatenate it with whatever I did in the first case. So check this out. So take our first idea. Let's take our first idea, but concatenate the expression 0 on the front. So if we do this, we end up with the expression. It's very similar to the one that you have. But you could just simply take the same idea and you just play around with it, right? So check this out. So I just have, so remember, in the first case, I have it where it'll start off immediately with a 1, but it ends with a 0. So I'm going to have 0. I'm going to concatenate this with what I had in the first case. So notice that it begins with a 0, but then I'm allowed to write 1, 0, 0 or more times, right? I could be 0, then I could go 0, 1, 0, 0, 1, 0, 1, 0, and so on. Man, when we get to the easier way of approaching this, you're going to feel so silly about it. I know when I first see it, I'm like, dang. But the main motivation behind what we're doing here is that if you deal with a more sophisticated regular expression, this technique might be more versatile than sitting and banging your head against the wall for like a good hour or two. Right, Miss Kitty? Yeah, Miss Kitty agrees. Sometimes exhausting cases, then simplifying later might be a good strategy to start off with. So naturally, we could do the same thing, but now we just got to do it with this second case. So to obtain, so similar to the previous case, so all strings that start with 1 and end with 1 and end with 1, well, all we have to do is just, okay, so remember, we want to have it where it is, what do we want? We want it to be a 1, then a 0, then a 1, then a 0, but we need to make sure we always count for just at least 1. But yeah, most certainly. But like I said, you can get actually both of them. But yeah, so I will get to the point of why, but when the empty string appears in one of these languages, as long as we account for it in one of them, we're okay. That's actually a really lovely question about the empty string. I'll get to that actually in one moment. So let's talk about that in one moment. So remember, I'm just going to use the same idea. So similar to before, all I'm going to do is have a 1. So I want to make sure it starts with a 1, but it ends with a 1. Notice in our second case, I can allow it so it goes 0, 1, 0, 1, 0 many more times, like this. But remember, each one of these is a set of strings. But now I have 4 possibilities. The strings that we have fit into one of these 4 buckets. And you might ask, Dan, how do you know this? How do you know that it fits exactly into these 4 buckets? And it doesn't have to be that they're disjoint, just to be very clear, because some of the strings actually sit in multiple buckets. My point is, how do you know that you've covered all of them? Well, remember, every binary string begins with a 1, ends with a 1. It may begin with a 0, end with a 1. It could be beginning with a 0, ending with a 1, and so on. But there's only 4 of them, right? There's only 4 ways that could happen. So as long as I count for all 4 of those, via cases, I've counted for all possibilities. So let's talk about this disjoint business. So So I must stress that technically speaking, they don't have to be disjoint. Because what we're going to do now, so this is the cherry on top of this. So notice that all the above here, so I'm not going to formally prove that these are all 4 possibilities that can happen. So what we're going to do is we just use union on all 4 cases. Thus, we end up with as follows. So to answer your question, if it mattered that, okay, this string is represented by this expression, but it must not belong to this other one, then the disjointness of their corresponding languages would matter. In this case, it doesn't matter that if 2 of the cases actually consist and contain the empty language. Not the empty language, the empty string. Don't mix those 2 up. It's okay if, say, epsilon appears in a couple of these. It's okay because we're just going to perform a union operation anyways. So what I was going to suggest is break it into cases. So here's our first case. There's the first case. There's our second case. I'm going to perform unions with all of these. So I made a much more complicated looking regular expression out of the 4 cases. So notice here that I have the 4 cases, but by using union, I have captured each one of them. So notice that if there exists a string that's in one of these, say for example, these 2 cases actually both contain the empty string. So in these cases, it doesn't matter because it's in here, but if I perform a union between the language of this one and the language of that one, they're both actually, it doesn't matter, it just appears again. And as far as we're concerned, it's just the set of strings in that language, the empty strings in there. It's in there, that's all that matters. Does that clarify the issue around like, okay, does it have to be disjoint or does it not to be disjoint? It doesn't matter. It actually doesn't matter in this case. As long as we account for it, that's what matters. But if we were, for example, instead of us trying to have it where, right, and keep in mind, our examples would be quite dramatically different than this one. The point here is I broke it into cases, and each case, they don't necessarily have to be disjoint in this case. They can overlap. As long as I account for them, though, that's what matters here, because the union operation would disregard the fact that duplicate strings exist in the first place. Yeah, so, but if it was, for example, that I wanted the first case to happen first, then the second one, then the third, then the fourth, and I didn't want to have it to have empty strings in a certain way, maybe I might consider it a little bit more carefully, but that's not the language we're looking at here. Now, you might look at this and say, Dan, that looks awfully complicated. But it most certainly would work. If it's unclear, you can always add more parentheses. So if you want this union operation to occur first, second, third, you can add parentheses. But in this case, it won't matter. That's just clarity on our parts. Because you just read it, you can read it, for example, left to right. But let me show you another way of thinking about the same language. And when I first seen this, I'm like, why didn't we just do this from the get-go? And the minute you see this, you might say, oh, Dan, why didn't we just do that from the get-go? And that's exactly where I'm going with this. It's because I want to show you that you can go about this in a much more complicated way if you need a more complicated regular expression. One common place where this pops up is if somebody asks you to detect a string that isn't a part of some other substring. Cases where you break it down like this might be worthwhile, because designing one just for like a very tailored one may take a very long time to do, but it might be worth it, but you have to start somewhere. That's the point I'm getting at. So let me show you a second approach with the same example. So we've seen that, okay, we can write out zeros and ones, and we can use the star operator, but you'll notice I didn't actually use the versatility of the regular expressions really a whole lot. There's actually a very, very lovely tool that we actually did not use at all when we came up with that regular expression. Do you recall that we actually have another regular expression, right? We have the regular expression for the set that consists only of the empty string, right? So this is also a regular expression. So we can actually use this to help us design a regular expression that's much simpler in terms of the length of its description. So here's another approach. And I want to show you this because it helps really open up the doors for how you can use epsilon in a regular expression. So check this out. Do you remember we had 4 cases, right? We had the 4 cases. It starts, remember we have it where it starts with a 1, ends with a 0. We also had it where it starts with a 0, ends with a 1. We also had it where it starts with a 0, ends with a 0, and we also had it where it starts with a 1, ends with a 1, right? Those were our 4 cases we had previously. Would it be nice if I could have it so that I have some way of optionally fitting these 4 possibilities in the appropriate spots? So that's where we're going to go with this. So check this out. Check this out. Is we can use epsilon to include an option. To include an option. So we can obtain a shorter expression. So let me carefully think about this with you. So check this out. Check this out. So we know how to come up with one where it goes like 0 and then 1, 0 more times, right? We know how to do this. This is one of the cases we actually had. And the reason why I brought this up when you were giving ideas for coming up with the regular expression, I thought you were heading in really a good direction, is because if you think about it, if I were to put a 1 right here, you would get 1, 0, 1, you have 1, 0, 1, 0, 1, 0, 1, right? You can keep repeating zeros and ones. But and the reason why I specifically picked it like this is, what if I can allow it so because remember, this will end with a 1. If I can allow it to include a 0 optionally at the end, that'd be great too, right? So check this out. So for this one right here, we'll cover this guy, right? That covers that second case we had. Because that's the one we had from this, I believe, the second case. If not, either way, it's one of the main cases we had. So what I'm going to do is check this out. So this is how I'm going to use epsilon. So watch this. So I'm going to allow me to pick between epsilon or the expression for 1. So you might ask that, you might be staring at that and be like, okay, so what the heck is that? What the heck is that? So let's think about this in terms of languages. So what the expression for epsilon is, remember we talked about it is just simply this set. It is just the set that contains the empty string. If we take that and we perform a union operation with this set, which that is the expression for 1, notice that this gives us just this language, right? The one with epsilon and just the string with just 1 in it, right? So notice that now if I have this gives me actually additional versatility, because when I want to concatenate that with the resulting of whatever this does, right? Then what happens is now I can pair it with epsilon or I can pair it with 1. So if you think about it now, this gives us an optional 1. So I like to think of the union operation like an OR. I like to think of it like OR. because that's quite natural to think about union, at least from a logical standpoint. You like to think of union like OR. So this gives you an optional 1. And then what should go right here then? So notice that if I have that there, this will actually cover my butt here for this optional 1. So now I could start the string off with a 1 if I wanted to. But also, I would like to have it so that, that I can get these two. What would you suggest I could put right here? Yes, that's what I'm suggesting. Is that we put right here, that's wonderful. That's actually really great. That's really great. As I suggest that we do this. Is we concatenate after this, we take and put this here, giving us an optional 0. So now notice that I can pick epsilon, then that means I can start the string off with a 0, and I can end it with a 0 if I wanted to. Likewise, if I take the optional 1, I do something here, and I take the 0 as opposed to epsilon here, I can end with a 0 here. So notice how this epsilon actually gives us an option now. Pretty nifty, right? Because it's all about how concatenation works. If I give you an empty string, you concatenate it with something, it's nothing, right? It gives you an option in this context. So it's just like, hey, look, you got nothing with everything that comes after it. So in the context of regular expression, we can use epsilon here like an option. So notice that this is much more concise than that one, but maybe not so much more, but it gives you some versatility. That's one thing I didn't really show you, is how you can use epsilon. So epsilon here actually gives us an option. So that's how very often you can use it in combination with union like this. So if you want to give an option for what symbol you might pick next, epsilon is your friend. Is that clear? So just remember, wherever necessary, include parentheses. So remember, the way you group these, oh yeah, I forgot to underline these two, very important. Those are technically our expressions that have concatenated. But yeah, so there's another approach. So notice here that I'm using epsilon to allow me to optionally select a 0 or a 1 in the appropriate spots. Sorry, I'm getting really excited here. So I'm just going to note here, just please remember about the parentheses. Because it's so easy to just be like, oh, I could just read it left to right, and then forget about that there's a precedence for the operators. So remember, star, concatenate, then union. That's the order from highest to lowest. Parentheses are your game changer that always is above that. It specifies ordering. Just like when we talk about an algebra, right? So whenever it's unclear, just use parentheses. So I thought it would be fun for us to do some more examples, because this one, we've been playing around with this. We've gotten a little bit slower. I thought it would be fun that we do, I think, at least a couple more examples. And then we see some, I would argue, more kind of applications-driven examples. Just so you could see, like, oh, I could use this to, I can, like, design a regular expression that does this sort of thing. And there, a couple of them are pretty neat examples that parallel something we've seen actually last week. So let me head over here. But are there any questions? Any questions about this example? I think we got a pretty good grasp on this one. But yeah, epsilon is your best friend. It gives you some optional, gives us some options. It's all about how that union operates. Okay. So let's do some more examples of designing regular expressions. So what I thought would be wise for us to do, because we've seen like I would argue was kind of cute, kind of basic, but at the same time it's fundamental. I think seeing how you can write out binary strings in a particular form is very important. But let's try to do something where I give you the language and let's try to come up with a regular expression for it. So let's try this out. So let's do some more examples. But now what I'm going to do is I'm going to give you the language. So we're going to consider strings. So we're going to consider all the binary strings. This is how I would describe that using regular operators. Such that, so this means such that W contains only one. So what we need to do is we have to come up with a regular expression such that if I give you a binary string, it has to describe only binary strings that only contain one. So for example, if I give you like a string that looks like this, that's okay. It only has one in it. One, right? Of course, it only has one in it. 0, 1 has only one in it. However, if it has 2 ones in it, not okay. Not okay. So let's think about what we could do here. So let's try to put into practice some of the things that we've seen so far. So far we've seen that we can use concatenation to bring together pieces that would make the form of a string. So I really want us to kind of take a big step back before we try to really put down ones and zeros. Let's think about what the string would look like if it were to get accepted, if we were to imagine this like a DFA. See, I caught myself there. So imagine I give you a string and I want to say, hey, look, I want to have it where it only has one in it, but it's not allowed to have 2 or more or 0 ones in it. So what would the form of it look like? Well, it would look something like this. So the form of it, so this is something you might get used to doing if you're thinking about regular expressions, is, okay, it has to contain 1. So you know the string looks like this. It's got a 1 in it, and there's other stuff. But what's the other stuff? What would be right here, and what could be right here? What could be over here? Well, there might be stuff, right? But notice it's not a 1, right? So we've got 0. I'm going to use words here because it gets a little confusing when you talk about zeros and then you talk about the literal symbol 0 versus a value 0. So we have 0 or more zeros here after the 1. And we have 0 or more zeros before the 1. So if we can identify the form that looks like this, notice that every one of the strings that would be in here has to have this form. Yeah. So notice that, yeah, exactly. So notice that it can have zeros or it could potentially be the empty string. Do you see that? So here it could be 0, 0, 0. It could be a whole bunch of zeros. It could be as many zeros as you want. But it also could be no zeros, correct? Just like we had in our one example over there, we just have a 1 just sitting there. So you might be compelled to use epsilon here. You might be compelled to use it in some way. You could, but you don't actually need to. Because let's think about this. If I have 0 or more zeros, well, what would that look like? It would be, you would have epsilon, you would have 0, you would have 0, 0, 0, 0, 0, 0, 0, 0, 0, right? So if I wanted this language, the language that consists of all of these, if I keep repeatedly doing this, what would that look like? So what language actually is this if I were to describe it in terms of regular operators? Well, let's think about it. Well, it would be 0 star like this, right? Well, that's at least what the language would look like, right? Because if I don't take this, it would just be the empty string, right? Then I could take 0 once, 0 twice, 0 3 times, 0 4 times, and so on. Well, let's think about what the regular expression for this is. Well, let's think about it. It's just, this one's really nice and easy. It's like our previous example, except it's even easier because it's just one symbol. Well, it would just be, let's see, this is for the set that consists of only the symbol 0, right? But I want as many of them as I can or none. So I apply the star like that. So notice that this is the key ingredient for what I've put right here and what I put after the 1. So what should the regular expression look like then? So what should it look like? So the resulting regular expression would look something like this, right? So this is the form that we would like, because that's what corresponds to this. So our regular expression will look like this. So we know there's going to be a 1. We need a regular expression for 1. And then before and after we're going to concatenate something. What should be right there? We're just right on the cusp of it. So we got what comes before and after. Well, we know we need 0 or more zeros. And we need 0 or more zeros after the 1. And boom, that's it. That's the regular expression. So notice here that I've taken advantage of the star operator to mean take none. So like in our previous example, we had it where we use epsilon to make an option. We don't need to use that in all these cases. Sometimes star is enough if you just don't need any of one. But notice that star is helpful for us if we need multiplicities of that symbol or groups of symbols. So, are there any questions about this example? So I thought this was a pretty cute one. I thought we would do another one that involves the length of the string next, because it's nice to see different properties about strings. So here we're counting. So notice that here, if I wanted to actually change this, so while you're thinking about anything interesting, notice that if I were to change this ever so slightly, so W contained 2 1s. Do you notice that you could just apply the same idea again? But notice that if I need 2 1s, notice I can have 0 or more zeros here, 1, 0 more zeros, 1, and then another 0 or more zeros, right? Do you see how you can keep applying this principle if I wanted to count certain finite numbers of occurrences like that? So you can see how you could generalize this a little further if you needed to. Pretty nifty. So I don't see any questions, so why don't we proceed to our next example? So I thought I would show us something about the length of the string, because it's helpful to sometimes think about different properties the string might have. A nice basic one is if the string's length is appropriate. So a nice one, mirroring some of the examples we've seen in the past about regular languages, would be asking a question about the length of the string. So let's consider this following language. Suppose I want to have, over the set of binary strings, I want to consider the following. Let's consider when the length of the string, so I'm going to denote that with these vertical bars. So the length of the string is equal to 2k for some integer k that is greater than or equal to 0. So please note that we would want to think about this very carefully, because notice it's k is greater or equal to 0. So that means that we can include several different kinds of strings as long as they have even length. So just as an example, since k can be 0, that means that the length of the string can be 0. There's only one possible string for that, namely the empty string, right? But we could also include other strings in this language. Well, it's corresponding, well, this language specifically. I was getting a little ahead of myself. I got 0, 1. So notice that this has even length because k is equal to 1 in this case. I can have it where I have a binary string like that. That has length 4. That's when k is equal to 2, and so on. But notice that it could be any binary string that has even length. So that includes the empty string because that's the string that has length 0, right? There's only one such string. So let's think about this carefully. So previously we had seen how we can effectively get options, right? We talked about how you can have it, oh, I want to pick a 0 or a 1. And we talked about this previously, right? So we said, okay, I want to have it where I can pick 0 or 1. So this would be the language that consists of only 0, 1, but I would like it to be so I could keep picking 0 or 1, akin to what I have here. So let's think about that first, before we get thinking about the star business, because we have to talk about the length of the string. Very important aspect that we have to figure out how that works. But we know how to do this as a regular expression. So this would be the language of the following expression. Right? So, yes. Yes, see, you're really right on the ball. I like this. That's where we're going. That's what we're going for. So notice that if I have this, that gives me my choice of 0 or 1. But as suggested in the chat, if I want to force it to have an even length, I want to combine this with an idea we've seen previously. So I want to be able to pick 2. So I want to pick 2 symbols. I want to do this 0 or more times. If I can do this, then I can recognize this language, right? I can describe it. I can describe this language. And there was a lovely suggestion in the chat for how we can do this. So let's tackle the pick 2 symbols part. So this picks 1 symbol. That picks 2 symbols. And we said to do it 0 or more times, right? And we've seen how star can be used to do that. And that's a lovely regular expression for this case. See, really catching on here, and I really like this. Wonderful. So let's see what else I got here. Let's do another one. So seems like we're really catching on here really well. But yeah, so naturally I can use concatenation. So I have an option, then another option, but I'm forcing there to be an option. If I want to include the ability to pick, say, the first one as an option, I might include an epsilon, but that's definitely not this language up here. So let's do another example. Seeing as now I've shown you one with the length, how about let's consider one with a substring. I think that's a pretty good idea. We see one with a target substring. So suppose that we give binary string again. I must stress that I'm just using binary strings to keep this nice and simple, but it's fairly easy to generalize many of the principles that we're seeing here. So say, for example, you're working with ASCII characters. It's just that now you just have more symbols you're working with. Or even alphabetical letters. So suppose let's consider the binary string such that W contains substring 0, 1, 0. So the reason why I wanted to show you this example is actually it's because it's more like an extension of one of the previous examples we did. So do you remember how we tried to come up with a form for the regular expression? So just as a quick example, just to show you what kind of strings would be fine here. Obviously, one that just has this in it, that's okay, right? If I had 0, 0, 1, 0, 0, this is okay because it's right there. However, a string like this, just with 1, 0, not okay. So let's think about it. Previously, we had seen how we can come up with a regular expression for... No, wonderful, wonderful. See, that's the whole point of this, is I'm trying to get to really cozy with this idea, just thinking about how you can formulate these. So let's think about this. Okay, remember how we had the example where we wanted to catch exactly 1, 1, right? So do you notice that it's very similar to actually this question if you think about the symbol, that 1, as this substring. So let's actually now revisit the same strategy we had before. So the form that we had, so let's think about a form for the string. So the form, we know for sure it has to have this in it. It has to have that in it. Yes, yes, exactly, exactly. So notice that now, what do you want there and what do you want here? Because notice it has to be somewhere in it. It contains it. It could be at the beginning, it could be at the end, it could be somewhere in the middle, right? So let's think about it. So here is going to be some binary string, right? So something before there's going to be a binary string with 0 or more symbols. There's going to be another binary string with 0 or more symbols, right? So now that we've seen how to do it with the contains exactly 1, 1, you can see quite quickly how we might try to do it here, right? Because it's just the same, it's the same concept, except now it's not just everything but the 1, right? It's just, so let's see what we would do here. So let's try to use the same idea we had before. So remember we have our target, so this is what we were trying to look for. So any string must have this in it. We know that. But now we have to have binary string with 0 or more symbols, right? We already seen how we can pick a symbol. We can pick a symbol, but I want to be able to pick 0 or more symbols. Then I do the same thing here, right? I was getting a little excited. My plus was starting to melt into something else. It looked like melted cheese or something. And there we go. Notice it's just the same idea, except now all we have, yeah, exactly. Exactly, very good, very good. So notice that it's just the same principle, but now instead of it just being a bunch of zeros, it's just a binary string. Lovely, lovely, lovely stuff. So hopefully you found these examples rather helpful. I thought we would be a good idea we see some trickier examples next. But these are going to be examples related closely to actually some things I've shown you before, but they also will help motivate some other ways you can use the regular expressions. So let's head over here to see a couple more examples. So we're going to apply the principles that we've seen up to this point, and we're going to try to see what we can do some interesting things. So these are going to be similar to examples I've shown in the past, and they're done deliberately to be similar to ones I've shown you when I was talking about finite or finite automatons. So I thought I would show you a couple more examples. Now, these are also help motivate a couple of the applications that you might run into out in the wild for regular expressions. Naturally, say in the case of searching bodies of text for certain key phrases. Likewise, also for design or certain analyses of strings. So, for example, you may have heard of something called a lexer. Generally, a lot of this regular expression business has numerous applications in text search, and along with compiler design. Like, it's all over the place. It's a helpful thing to be aware of. That's what I'm getting at. So I thought I would show a couple more examples. Now, the main reason I want to show these examples for you is because we've actually designed epsilon NFAs for these. So these are non-deterministic finite automata with epsilon transitions. So I want to convince you that we can come up with regular expressions for those finite automata. So instead of me talking about just a machine, I could describe to you the regular expression for which describes the same language that that machine would recognize. And you'll see that there's actually something interesting going on. So we're going to revisit a couple of ideas here. So first, we're going to talk about recognizing key phrases or keywords. So I want to remind you of the scenario. So don't worry if you haven't seen these before, don't worry. I'm just going to rehash everything. So suppose that you are typing on a keyboard and you have some key phrase that you're looking for that is the most recently typed part of the string. So imagine you're keeping track, say you're logging the inputs from the keyboard and they're being typed into a box. And I would like to know if the most recently typed sequence contains the key word. So this would be at the end of the string, because that's the most recently typed sequence part. Well, you think of it like I'm just logging this and it's just appending on the end of the string that I'm keeping track of the most recent phrase that's been typed in. So I'm going to suppose my alphabet or my symbols are going to be A, B, all the way up to Z, which is something that you would run into most certainly if you're playing around with text parsing and things like that with a regular expression. That's most certainly the kind of situation you'd run into. So I already started with suppose. So let's design, but these looking a little bit concerned. Let's design a regular expression. I'll just abbreviate it as regex. Regular expression where strings end with the word Pam or no. Don't ask me why those are the words, but those are just the words. The principle should easily be extendable to other cases. So if there's like and I talked actually about this a little bit in the intermission, was this idea that you could, for example, like have a text-to-speech program. You can imagine that you have a list of words that you would like to detect. But in this scenario, you would imagine as this would be the most recently typed part of the string that would be part of the logging of the keyboard inputs. So this would be like right at the end of the string, and you would imagine it's like annihilating the stuff that comes much before it. So you'd have some like set length, and you would imagine that you're looking for a string that is the most recently typed part of it. So this would be at the end of the string. That's at least what I'm going with for the example. So let's think about how you design a regular expression where the string ends with Pam or no. So let's apply the principle that we've seen before. So we've already seen that we can have it where it starts off with some options for symbols that can be typed in, but it has to end with Pam or no. So we know how to get that kind of option first. So let's think about the form of it again. So you would have any of A, B, C, all the way up to Z, 0 or more times. So there could be stuff here before that. But you know that it's going to be Pam or no right here, right? Has to appear. That's kind of the form of this. So let's try to put this into some plain, put it into our regular expression. Yes, that's exactly what I was looking for. Bang on. So what would the resulting regular expression look like? Well, let's just put it into the form. Perfect. Perfectly done. So I have regular expressions for each one of the symbols, and then I group them all together with union operations, put it all together. And then I naturally put a star on this because I want to be able to do this 0 or more times. So I pick one of these symbols 0 or more times. And then naturally, I concatenate this. Whoops, I don't want to underline all of them because they're all technically different symbols. I have Pam or no. But it's right at the end. And that's the regular expression. Yeah, you bang on 100%. Awesome stuff. So notice here, this will detect it at the end. If you wanted to have it so it just contains Pam or no, you would just take this and just throw this also at the end too. So you just concatenate that onto the end. One thing I should mention as sort of a convention as well, and some actually in some libraries it works sort of like this as well, is that if ever you need to like just access the whole all of these symbols, you could just simply, instead of writing all of this, some people would write just this. You would just have sigma star like this, which is quite natural. Then you would just have Pam, union, no, like that. Some people might write it like this. They might emphasize this with the dot for the concatenation, but anyways, that's another way of writing the same thing. Some people would write it like that. I prefer trying to exhaust it all out for you, but most certainly this is just another way of writing the same thing because you already know sigma star is 0 or more symbols from that set, right? So anyways, that's one example. Just detecting keywords, rather nice thing to think about. How about reading decimals? So imagine I give you a bunch of digits that are supposed to be for a number. Now we've seen this rather, I don't know, it's a classic example. It's actually from a book by Hopcroft et al. It's a classic. For reading decimals. So we're going to come up with a regular expression that could recognize like it has the form of a decimal string. So this one's going to be a little bit trickier, but I'm going to show you using regular expressions that we can actually express it quite simply with the use of variables. So just to recall, I'm going to recall that this is going to be what we're going to look for. And I do not claim this to be like the perfect way of detecting a decimal number. Just to be very clear, this is just an example of how you might detect a decimal number. So this just has a particular form. If you don't like this form, I encourage you to think about other ways you can formulate a decimal number. So recall recognizing decimal numbers. So we're going to imagine we have symbols, one for each one of the decimal numbers. So when I should say not decimal numbers, I should say digits. So we have 0, 1, 2, 3, 4, 7, 8, 9, all the way up to 9, yeah. You would have 0 all the way up to 9. So you have symbols for each one. Sorry, I'm just having a blast over here. I'm really enjoying this. So we want to recognize decimal numbers. They're going to have a specific form for this example. So they're going to have a form as follows. So here's the specifications for the form of this decimal number. So it's going to have an optional plus or minus sign. So that's the first thing. Let me put a 1 here. Then we're going to have 0 or more digits. Zero more digits, a dot, then a string of digits. So this has to have at least 1 digit, just to be clear. In this case. So it's going to have to be that has the following form. So it's going to have 1, then 2, but it's also going to be actually that it can do one of 2 things. So instead of it being that it's just 1, then 2, then 3, I'm just going to have it so it's 1, then 2, or 3. So the minute you see or, that tells you right away you might want to use union. So here we go. So you're going to have 1, then you're going to have 2 or 3. That's what the form is going to be. So it's going to be a string of digits. It's going to have at least one digit, just to be very clear. A dot. Then 0 or more digits. So that's what the form is going to be like. So, so anyways, first, I'm actually going to, instead of looking at this like I'm just going to try come up with one right at the beginning, now that I've laid it out like this for you, I want to really emphasize that, okay, I have this is an option, but I do one of these. So naturally, I've actually broken down really 3 steps for you. The first one is an optional one, then you pick one of these 2. Right? So if I could come up with a regular expression for this, and then I come up with a regular expression for this, and a regular expression for this, as long as I can compose together the form as per the instructions, I can come up with a regular expression for all of it. So that's what I'm going to do. So sometimes if it's really complicated like this, I would argue this isn't terribly complicated, but it's a good example of how you might try to take regular expressions and combine them with other regular expressions. So let's start off with, first let's look at 1. So let's look at 1 first. So suppose I want to come up with a regular expression that will just simply allow me to have it where you put a plus, a minus, or nothing. So you can think of this like if I had positive 2.0, I would like to have it so I can put a plus here or a minus or just nothing. So it could just be 2.0. But I would like to only consider just this first part. So I would like to have it where it's optional plus or minus. So the form of this would just simply be plus or minus or nothing, right? So what would that look like as a regular expression? So I'm going to actually give it a name. So remember, we had a technique for how we can include an optional symbol. So I'm going to give it a name. I'm going to call it E. So what would this expression look like? Now, it's really hard to type it in, so I think it would be a good idea I kind of walk you through it. I know that probably somebody's just staring at this for like, Dan, I already know how to do this, right? Well, suppose I have a symbol for the plus. This is going to get a little confusing because we have plus for union, but it's going to be the plus sign as a regular expression, union, the minus sign or negative sign as a symbol, with its as its expression, right? So this is the expression of the minus sign, or I have the option to not include either of them. So that's 1, right? So that seems pretty darn nice. So far I have that. Like I said, it gets a little confusing. That's why I'm using these underlines to help us emphasize which things are the expressions, which things are the operators, with the exception of epsilon and the empty language. So let's look at 2 next. So let's look at 2 next. So I'm going to call this F. So let's put all the stuff we know together to try to figure out this one. So it says 0 or more digits. So remember the digits are for us are 0, 1, 2, all the way up to 9. So those are our available symbols. Then we also have a dot. So dot is something we also have access to as a symbol. So let's think about how we'd put this all together then. So it says 0 or more digits. So the minute you see 0 or more, that tells you probably star is going to be your best friend here, right? So I'm going to have 0, 1, 2, but I'm going to put unions between all of these with a star, right? That's the first thing that kind of sticks out at you as like a sore thumb. 0 or more digits and a dot is coming after this. But note, just to be very clear, I'm going to underline it to make sure it's very clear that that's a symbol and its expressions, because this dot is not concatenation, right? It's a decimal. This is why I underline them or boldface them in my notes. It gets very confusing otherwise. Now, Now we need to have a string of digits, but we need at least one digit. So one way we could do this is come back to one of our previous examples where we needed to have at least one symbol of a particular form. So I'm just going to include a mandatory choice of one of the digits. Then I'm just going to use star on here. On this last choice. So this right here will force there to be at least one digit. And then I can have 0 more after that. I think that's pretty nice, right? One remark I will make is that if ever you want to say 1 or more, some libraries will support this, but there's also a formal way of writing this. Instead of writing star, you would use plus as the exponent. So some would refer to it as plus. That is 1 or more. So the equivalent way of writing this last part would just simply be where you would not have this right here, and you would have a plus right here. But I'm just going to keep it simple, just talk about star. But some libraries actually do support that functionality. Okay, so that's that one. Now that we have all the bits and pieces for the second case, let's just put them into practice. I'm just getting so excited the words are just slipping out of my mouth. Let's get the third one here. So this one is very similar to the previous one. So it says a string of digits, at least one digit. So we're just going to use the same idea we had here. Just put that right there. With a star. Then we're going to have our regular expression for the dot symbol. And then we're going to have our 0 or more symbols that come after it. Boom. There we go. There we go. Now, I believe I've got that carefully. Let's see. We got our at least one digit on the side before the decimal. Then we have 0 or more after that. There we go. So the reason why I want to show you this example, other than the parallel with the epsilon NFAs that we've seen previously, is that I want to show you that if you have multiple steps like this, design the regular expressions for the smaller steps, and then you can use regular operators in the form of the regular expressions corresponding representations of those operators to express the more complicated one. So let's take a look at what this would look like. So it says optional plus or minus sign. So that's E. So our regular expression would look something like this. You know it's going to start with E. Then what comes after this? We have 2 or 3. So you got a choice of 2 or 3 that comes after. Which one, what are we going to do? So remember, I have these represented as variables now. So I can use these names as opposed to writing out all those big complicated things over there. Well, if I want to choose 2 or 3, notice that that's the same as me having F plus G, right? So putting this all together now, I have 1 that happens, then I pick 2 or 3. So I concatenate this with F plus G. And boom, there you go. So you can design the regular expressions or come up with these regular expressions for more complicated cases and use the regular operators to bring them together into a particular form akin to this example. One thing I will point out is that this is very interesting in several regards because the epsilon NFAs for the first example and the second example, they have very similar kind of structure to them. Namely, the epsilon NFA that we had in our first example had it where we had these pathways that would have the key phrases, but it would have it so we can keep producing more guesses. This is very, it should remind you of something that looks kind of like that we had over there. And over here we had two pathways that would split off. And that was only because of how similar these two cases here are. So we kind of specially designed it to handle these two cases. But it's almost like I had the choice of one or the other. Very interesting, right? So are there any questions? Any questions at all? Any questions? Any questions? Because I'm going to lay some interesting things on us next. So, excellent. So as I mentioned, actually you can use an example akin to some of the things I've shown you here for designing regular expressions to prune out certain key phrases. So I actually mentioned this near the beginning of the lecture, and I mentioned it a couple times, like if you take say like my first example here, and you just extend it akin to what I described, you can come up with a regular expression for identifying certain key phrases or keywords. So just an example, if you're working with text-to-speech, for example, and you're looking for a certain keyword, it'd be something akin to this that I have on the right board, which I'm going to move over to in a moment. So you might ask, Dan, why are you bringing up examples about epsilon NFAs? Well, I'm going to be talking about a rather insightful but important construction that's going to put and kind of stitch a lot of what we've been talking about for a while together. So let me just erase the board over here, but I'm going to sketch out something rather important that's going to set up kind of the course of action for the next week or so. And I tell you, it's really something. It's like when you're a kid and if you're part of my generation, it's like Saturday morning cartoons. This is like the exciting preview that comes out and you're like, oh my, I need to see that. This is kind of that. But I am planning to, we'll see, what time are we at? Okay. Seems like we got some people interested. We got actually a pretty interesting thing I'm going to be talking about here next. I actually am going to break this into two parts. That's why I'm saying I'm going to give you a nice preview of everything, of this whole thing, because it's going to bring everything that we've talked about for quite a while together into a nice bow. It'll characterize effectively what we've been talking about for the last month, all into one theorem and I want to show you this because I personally really love this construction. It's also a rather important construction that you can algorithmically use to take some of the things we've talked about with regular expressions and build actual machines, okay? So this is not anything that I would consider esoteric or anything like that. This is often, I would argue, some of the heart of some of this technology if you think about it as a technology. And this is the big thing that kind of like when people talk about Stephen Colcleany and a lot of the automata theory that goes into compiler design, this is like one of the canonical examples of things that people talk about. And they say, it's like, Dan, should I learn about theory of computation? This is one of those kind of like bookmarks that you would put in your book. And you say, Dan, this is something I might want to revisit one day. Because at least theoretically, it's theoretically interesting, but also has serious practical implications. So, and that's often I would consider the best kind of computer science is when it's theoretically interesting. So it answers a question about computation itself, but two, it also manifests itself in many different facets of computation. So some would think of killer applications for these sorts of things. I think of it as it encroaches into several different problem formulations. And that's the kind of stuff that gets me really excited as an algorithms person. Because once you see how you can study one problem and you can look at it in a completely different other way, and that stuff is mind-blowing when that happens. And I mean, some of the stuff that I'm talking about here, people have gotten Turing Awards for some of these things. So I'm just saying, it was really that mind-blowing. So I'm just trying to make sure I got all my notes in order, okay? So otherwise this is gonna turn into some fun, okay? Okay, so let's get into this. Indeed. So let's get into this. So we're going to be talking next about what I would consider one of the core pieces of some of the building blocks for automata theory that we've been talking about up to this point. I'm going to call it this, but it must stress that it's called and manifests in several other different ways. So I'm going to be referring to it as Claney's theorem, an attribution to Stephen Cole Claney, and much of the theory that said logician came up with in relation to regular expressions and regular languages and regular operators. So here's the theorem. But I must stress this isn't the only way of writing out this theorem, just to be very clear. I'm only putting it in the context of what we've discussed. So a language L, I already am getting excited. A language L is regular if and only if there is a regular expression that describes L. That is, the languages described by regular expressions and finite automata are regular. Boom. So here we go. So what this theorem describes is actually a characterization of the regular languages. Now, when I first defined the regular languages to you, I said that we call a language regular if there exists a deterministic finite automaton that recognizes that language. What this theorem tells you is that actually it's also that there has to exist a regular expression that describes that language too. But also, I've also given you other equivalent formulations as well, right? We previously had proven that there exists a non-deterministic finite automaton that recognizes a language if and only if there is also a deterministic finite automaton that recognizes that same language. And we talked about also the same thing for an epsilon NFA as well. So this characterization is widely attributed as Claney's theorem. That's what I'm referring to. So here's how generally this proof tends to go. There's several ways you can go about it, but here's the way I'm going to go about it. To prove the claim, we use the following framework. So here's the picture. So I'm going to give you the picture. And we're going to be picking up and using pieces that we've established actually in previous lectures. But there's some pieces that are missing. Those are the pieces that are missing to prove this theorem. So just as a reminder, just to kind of give you a big picture of everything we've done up to this point. So we talked about how deterministic finite automata, those recognize the regular languages, right? We also proved that these NFAs, that for every DFA, there is an NFA that recognizes the same language. Likewise, we already established that for any NFA, there exists a DFA that recognizes that same language. This is something we had proven in the past. Now, this part isn't terribly relevant for our theorem here. However, that is another bridge you can cross for proving the theorem. What we're going to do instead is I'm going to be using the fact that we had shown, or at least I gave you the sketch or reasoning to prove that for any epsilon NFA, there is an equivalent DFA. We established this through the subset construction, right? We talked about the lazy subset construction where we allowed it to have the epsilon moves and we accommodated for those. So for any epsilon NFA, I could show you there's an equivalent DFA that recognizes the same language. So here's the two missing pieces. So first, the main part of this theorem involves regular languages and regular expressions. So there's two parts to this. The first one that I'll point at is that for any DFA, there is an equivalent regular expression that it describes the same language. Likewise, for any regular expression, there exists a way to construct an epsilon NFA that recognizes the same language that regular expression describes. So I describe them as the first and second. Instead, I'm going to refer to this as the first part. And the first one I described is the much trickier part of this proof. That is what I'll refer to as the second part. So you might ask all the pieces, just to kind of recap here. So here, this is characterized by the subset construction. We've already seen this. So if we have 1 and 2 in place, then what happens to establish the claim that I have up above? One way we can do it is that if I give you a regular expression, I could show you. So remember, it says the language L is regular if and only if there is a regular expression that describes L. So if we've defined that regular languages are those that are recognized by a DFA, then what I do is I take a regular expression, convert it over to an epsilon NFA, so build one, then I know how to turn it into a DFA. So since I already have established this point, then I can go from a regular expression to a DFA. Then the other part of this proof is to show that for any DFA there exists an equivalent regular expression that describes the same language this DFA recognizes. So once you have this in place, we can establish this theorem. Is that clear, everybody? So this is what I'm characterizing as Kleini's theorem. Okay, so there's two parts to this proof. I'm going to be showing you next the first part. And this is arguably one of my favorite things to show when I talk about automata theory. So to do and establish one there, I'm going to present to you something called Thompson's construction. It's very often called Thompson's construction. Sometimes it's also called McNaughton-Yamada-Thompson algorithm, named after the people that are often attributed for the discovery of said algorithm or construction, however you would like to describe it. So, just as a remark, some will call this Thompson's construction. So with this, you can take any regular expression, build an epsilon NFA out of it. But I'm going to describe it within this theorem. So this will establish one part of the proof, number one that we had over there. So if language L is equal to the language of R for a regular expression R, then there is an epsilon NFA E where the language, where L, so So L is equal to the language of E. So that language L, so basically what I'm saying is language L is equal to the language of R. Okay, so at the heart of this proof is going to be the description of Thompson's construction, which I would argue is a fundamental algorithm should you be interested in converting regular expressions over to the finite automata. So suppose language L is equal to language of R for some regular expression R. We build epsilon NFA E where L is equal to the language of my epsilon NFA E, and it has the following properties. So these two properties are going to play a very large role in how we can prove that Thompson's construction is in fact correct. So these two properties are going to be, what's that word for this? It starts with an I. Starts with an I. We use this all the time in algorithm design. When we want to establish the correctness, sometimes this is a very helpful tool. It starts with an I. We're going to have two invariants, and we've used this technique before, so I'm going to hope that you get the idea of where we're going with this. These are two properties that are going to be upheld as this construction is being played out. So watch this carefully. So E has one final state. So one final state. There are no arcs, so those are directed edges or transitions. So no arcs leaving this state. So it has one final state, but there's no arcs leaving that state. So there's no transitions out of this specific state for E. Then the reason why I deliberately use the word this state is because the final state as we construct the epsilon NFA may change. And the other one is rather important, is there are no arcs transitions, as I mentioned. The arcs are transitions. If you think of it as a directed graph, arcs are transitions toward the start state. So we're going to be now characterizing the definition that we had for a regular expression. We described it inductively. I can also think of it as a recursive definition as well. So I'm going to think about it recursively. So I'm going to describe this construction in terms of building an epsilon NFA. I'm not going to explicitly describe it in algorithmic terms. Instead, I'm going to describe it as a construction, hence why I'm referring to it in this manner. But it's going to be important that this construction has these two properties along with this one, because these are going to be very helpful for us to establish that indeed what is happening is happening. Okay. So does everybody understand the game plan? Everybody understand the game plan? So just remember, this simply means that if I give you, suppose that there's a final state, you can't have it where there's transitions leaving this final state. That can't happen. And there's only one of them. And this one is saying that there are no, like say if this is the start state, there's no transitions heading towards the start state. So we use the recursive definition of a regular expression to perform induction perform induction. So we're going to proving with mathematical induction. We're perform induction on the regular expression R structurally. So we're doing structural induction. So if you've never seen an example like this, these are really a gem when you see them. Structurally, ensuring properties 1 and 2 hold. So, you might ask where we're going with this. So naturally, I'm going to describe the construction very similar way that I would describe how we talked about a definition for like a finite automaton. So I'm going to have a basis and I'm going to have an induction part, but I'm going to embed within the description of the construction its proof. So for any little details here and there, I may omit those smaller details, but may orally only state them. So I'm just going to try to keep this concise. I normally like to go into a lot of detail, so that's why I mentioned this. So here we go. Here we go. So let's start off with the basis. So recall that there's actually 3 parts to the definition of a regular expression. So there are 3 parts to the basis of a regular expression. We build E in these cases as follows. So check this out. Check this out. So we had 3 possibilities that can happen for the basis definition of the regular expression. Do you recall what they were? We had it where are they? They are epsilon, empty language or empty set, and when we had a single symbol, right? So we're going to have corresponding epsilon NFAs for those 3 cases. So I'm going to lay them out in the same order I gave them to you when I defined the regular expression. So for the first one, which is this one, here's how I would construct the epsilon NFA. I'm going to look at it like building blocks, okay? Imagine I'm building this really epic structure, like say like an Egyptian pyramid set from Lego or something like that. Don't come after me, Lego, bro. We're talking about automata theory. But imagine you have this big, complicated Lego set. And you're right at the basis. So imagine you've decomposed the regular expression into its most fundamental parts. We're going to start at those most fundamental parts. So you imagine you have this really big construction, and as you're going down, you're building intricate these parts until you eventually get down to this case. So it's going to feel like you're building bottom up the construction. At least the way that you might do this by hand. Or you can also view it that way as well if you'd like. Like I said, induction, recursion, they are 2 sides of the same coin. So we're going to have 2 states. We're going to have the start state be this one. And then we're going to have a transition from the start state to this final state on epsilon in the first case. You'd agree with me that this would, if I gave you the empty string, would accept on the empty string, correct? Because notice that I'm in the start state, there's an epsilon move, I can go right to the final state. Next one, for the empty language, or empty set. Well, all I'm going to do is I'm just going to have it where you have 2 states again. Have a start state, but no transition to the final state. It's just going to sit there. Do you agree with me that you're never going to be able to get to this final state? Yeah, you're not getting over there. There's no transitions to the final state. Now, just please remember those two invariants that we had in mind. So that E has one final state, and there are no arcs leaving this state. So notice there's never arcs going out of here, and nor are there transitions heading into this start state, okay? So please keep that in the back of your mind. So next we have the one for the symbol. I bet you could help me with this one. So again, two states. This is going to be the start state. Suppose it's on a symbol A, like I have over there. Suppose its symbol is called A. What should go right there for the transition? So suppose I gave you the corresponding language for this one. So design an epsilon NFA that accepts on that string. What should go right there for the transition? Just A. So you do this, so if, say if it was a different input symbol, you would just put that input symbol there. So, you might ask, what the heck is going on? So, in the first case, we have expression epsilon. We have the second case, we have expression empty language or empty set. And then this third one is the expression A. So, to accept on string A, there has to be a transition on symbol A, right? So, each of these corresponds to each one of these regular expressions. I'll let you convince yourself that the invariants are holding based on the explanation I gave you here. So far these seem rather nice and straightforward. I don't like using those phrases, but I've already given you some justification why these would be, in fact, correct. So now I'm going to provide I would argue is the fun part of the construction, where this really can get out of hand if you're trying to doodle this out. So here we go. So assume the statement of the theorem. Theorem holds for the intermediate sub-expressions of the regular expression. Sub-expressions of the regular expression. So just to elaborate what that means, because that's a lot of heavy lifting that I just wrote there. That's a lot of heavy lifting, at least mathematically speaking. I use the M word. It makes a good sandwich, the mayonnaise. So let me break this down, what I mean by this. So what I'm actually saying is the language of these immediate sub-expressions. So you just got to imagine I have the regular expression. Imagine there's other operators that are occurring within the regular expression. So imagine it's being decomposed into those smaller constituent parts. That's what I'm referring to as the intermediate or immediate sub-expressions. Intermediate are all the ones that happen as you're evaluating the regular expression. That's at least one way you can think about it. Languages of these immediate sub-expressions are also languages accepted by an epsilon NFA with properties 1 and 2. So now, if you're willing to accept this step in this process, so in plain language, what this is saying is you imagine you have yourself at a given step of evaluating, like, or parsing or understanding the regular expression. So you imagine you have your like variables and you have a regular operator in between. You imagine those two parts that have been considered up to this point that have epsilon NFAs, they indeed do. And now I want to see what happens when you build up to the next part. You think of it like a very bottom-up process. So imagine I start off at the most fundamental parts, I build up an epsilon NFA from those smaller constituent parts. Each of those intermediate steps in the process of considering the entire regular expression will each have, in those intermediate parts, an epsilon NFA. So I'm going to show you how each one of those happens, okay? So what I have to do is establish for you that if I give you two constituent immediate sub-expressions, so these are ones that you've just built epsilon NFAs for, I'm going to show you how to get the next epsilon NFA in your construction. So imagine you have like a whole bunch of these kicking around. I show you how to build the next one using a union operation, a concatenation, or a star. So that's where we're going with this. I assure you that it'll make a lot, if this is a big jump for you, once we see the example, it'll hopefully clarify what's going on. Okay, here we go. So, for each regular operator, presume R and S are some smaller sub-expressions. I'll say smaller expressions wherever applicable. So akin to what I just described a moment ago when we were discussing over there. Wherever applicable. So naturally I have to go through our regular operators. So let's check out what happens. Now, rather than going through delicately writing out the arguments, I'm instead going to include them in my notes. I'm going to show you the construction and I will verbally or orally describe to you why it's correct. And the explanation in the notes provides how you might describe this as in a proof. So the first case we're going to consider when we have a union operation between two regular expressions. So what are we going to do? So here we go. This is where I get to draw some fun pictures for you. And I must stress, the pictures are not the proof. It's just to describe to you the construction. So as I have R and S. So here's now remember, R and S by the induction hypothesis, each one has an epsilon NFA. And each one satisfies invariant 1 and invariant 2. Did you notice that, by the way I was designing the epsilon NFA in our proof, that they always had like kind of like an entry state and a leaving state or final state? Like basically there's one at it was its old final state before, now I'm going to build a bigger one. So check this out. So here we go. So whenever there's a union, we're going to have two paths. We're going to have paths. So I'm going to create a larger epsilon NFA out of those epsilon NFAs. So I'm going to build a larger epsilon NFA. So I'm going to have epsilon moves that take me to either the epsilon FA for R or the epsilon FA for S. And then I'm going to have a new final state. Now these are no longer final states. They were final states before, but now they're going to be states where you can leave on an epsilon move to this new final state. So notice that now the final state is this new state I've created. But now those are no longer final states. Now they're just states that you're going to leave on an epsilon move to this new final state. But now notice, as a result of doing that, we have exactly one final state. And what can you notice about the start state and the final state? What did we need to establish? We need to make sure that there's no transitions leaving the final state. That's actually why we need this final state to be the only one, right? Because this would be, there's a transition leaving that state, which would have been the original final state, right? Likewise, there are no transitions heading into this start state that I've just newly created. Did everybody see that? So now notice, I want you to think about this using the intuitions you know about for finite automata. Imagine I give you a string. For that regular expression, remember, the regular expression is a declarative way of describing which strings get accepted by, the intuition here is for the epsilon NFA, you imagine this is a string that gets accepted by the epsilon NFA. But also, you can think of it as all strings that are described by the language of the regular expression, which is the same idea, right? Well, look, you can go this way. So notice that on an epsilon move, now you have all the transitions that might happen in here for that epsilon NFA that would take you here. If it's accepted, it would be right here, right? That's what has to happen. But now we have an epsilon move that takes me right here. But please remember, there's no transitions leaving out of this state either, right? So it can't be the case that there's like some funny business where like it can go to a different state inside here and then suddenly there's a bunch of problems. No, it's because of the way the invariant operates, right? Because any string that would be described by that regular expression would be a string that gets accepted by the epsilon NFA that is described by this box. So that means that it would have to have got here and accepted for that string. But now I have an epsilon move, takes me here for free. So I can get to this state, accept. Or I could move to these states over here and do it on S. But do you notice that this actually exactly characterizes what language? Characterizes this language, right? So notice that the epsilon moves characterize an OR, akin to when we talked about epsilon, when we talk about our regular expressions, right? So notice it has a very similar parallel going on here, but so notice how the union operates like a choice, just like it does for the epsilon NFAs. So notice that variates 1 and 2 hold, and indeed, it gets you the desired language as a result. Let's consider the next one. Let's consider when we concatenate the two regular expressions. So what's this going to look like? Check this out. So next we have this. So remember I have R and S. Remember, by the induction hypothesis, I have epsilon NFAs for R and S that satisfy the two invariants. So what I'm going to do is I'm going to take them just like two blocks. I'm just going to like connect one up to the other one. But instead of making it so they have two paths like this, two options, instead I need to force it to go through R to get over to S, right? So how am I going to do that? I'm going to make the start state of my new epsilon NFA. It's going to use the start state of R. R is epsilon NFA, then you know that to get here, because of the invariant, it had to have been because that string belongs to the language of R, right? Otherwise, it wouldn't have accepted it, right? That's true for this epsilon NFA that I've drawn in this box, right? Well, to accept any string that would be the result of R concatenated with S as the regular expression version, that would mean that it would had to be some string that would be a part of the language of S. Well, here's an easy way to do that. You force it, you pipe it through R, then you force it on, then you allow it to, on an epsilon move, to go to the start state of S, and then you make the final state be the final state of S. So notice that I am forcing it to go through R to get over to S. But the epsilon move is what I freely use so I don't consume any symbols for my epsilon NFA. So notice that this, as a result, gives me that. Most certainly, right? But it also maintains the two invariants. Do you see that? Notice at the start state, there's no transitions heading into the start state, because remember, that property is satisfied by the epsilon NFA of R, right? There is no transitions into the start state for R. So you know it still is held for this new epsilon NFA. And also notice that there were no transitions heading out of the final state here, because that was true for S. So we're okay for case 2. Case 3, we have R star. So suppose I give you R and I want to perform the star operation. Now, this one I love drawing because at first it just looks like some hooky dooky doodle, okay? So hooky dooky doodle, okay? So here we go. So I have R. So imagine I have the epsilon NFA for R. In this case, you have to get careful when you're proving this. I think I broke it up into 2 cases for the proof here. You'll see why in a moment. So I have R, so the epsilon NFA of R. I'm going to introduce 2 new states outside of the epsilon NFA of R. So these are going to be part of my new epsilon NFA. The final state is going to be this one. The start state is going to be this one. And what I'm going to do is as follows. Now, do you remember that the star operation allows me to pick it 0 or more times whatever is going on with that regular expression, right? So I can not do it at all, right? I can do it not at all, right? Or I could do it potentially 1 or more times, right? So I'm going to transition on epsilon. So make an epsilon move that goes to the old start state. And then I'm going to have whatever's happening in R, whatever. The final state, it should allow it to go over here, right? Because it might read the string once, the desired one, or it might read it multiple times. But this is the trick. How do I get it to do it multiple times? Well, remember, use the intuition you know about finite automata, okay? Because of the invariant, you know that there's no transitions heading out of this, what used to be the final state of this epsilon NFA. No transitions heading out of it. There's no transitions heading into this one either. This is where the invariant becomes very relevant for us, because we know this as a matter of fact when we're building the epsilon NFA, right? So, what can I do then? There's nothing heading out of here. There's nothing heading into here. That means that when I perform, I follow a pathway in here, which reads the symbols, right? It reads symbols. It gets me here. In the original epsilon NFA, it would accept right here, right? It accepts right there. And now, because of the epsilon move, I can get here freely. No worries. So let's take advantage of the fact that there's no transitions heading out of this state and no transitions heading into this state. So if I want to allow it to read more occurrences of a string that would have been accepted by the epsilon NFA, I just make an epsilon move that connects from the old final state to the old start state. So in the way I describe this to you, there's two cases that can happen. It could be the case that you follow this pathway. In that case, this gives you when you make no choices. Versus this one, where it permits you to make one or more choices. Namely, in one case, you end up with what language? You end up with just selecting, it would be for when you have the empty string, right? Otherwise, you have it where you can get LR, concatenate with L and R. And then you can keep going like this, right? Because you can keep following that epsilon transition right here. So again, I'll leave the proofs written aspect of this argument in the notes. So, believe it or not, since we've established via our reasoning that each one of these satisfies invariants 1 and 2, and they also indeed are identifying the corresponding resulting languages that would be expected for the epsilon NFA versus the regular expression, we have completed the induction step. So I'll leave those details in the notes. And let's proceed. So all you do now is you would apply our best friend involving mathematical induction, and that would complete the proof. So now what I want to do is I want to show you an example of applying the construction now. So now that we have the key ingredient, so remember those 3 pictures over there. I normally get people to remember them. so keep them in the back of your mind, okay? So let us build an epsilon NFA from the regular expression 1 or 0 star 0, so concatenated 0, concatenated with 1 or 0. So I think this is a pretty nice example to start off with. It has a few different pieces. It has, first, it has all the operations in present. So I'm just to make things easier for us, I'm only going to indicate the final state and the start state once we're done the construction. But I must stress that as you're doing this, you'd periodically swap what the start states or final states might be as you periodically make this. Well, you increasingly make this epsilon DFA. Okay, so let's check this out. So let's start off with what's going on in here. So we got our bits and pieces here. So we got 1 or 0. So we have these 2 pieces, right? So again, like I said, I'm going to omit including the final states, but these would be the corresponding epsilon NFAs for 1, 0, and now I got to perform the union. What's the union? Remember, we create the 2 pathways with the epsilon moves. And then we have epsilon moves that leave the old final states over to this new state I've created, which would be the final state if I was finished. Now, I'm not quite done yet. So notice that I have this. Next, I need to be careful though. Wait, I think I'm supposed to have a star over there. Let me just put the star back in. For some reason, I didn't include the star. Let's get the star. No, wait, never mind. We're okay. We're okay. Okay. So now that we have this, do you notice that this is actually what I have right here? This is actually how you'd apply Thompson's construction onto this regular expression right here. Do you see how I've taken those sub-expressions, namely 1, 0 here, those are the epsilon NFAs, and then I'm applying the induction step from our proof over here. That's how I get this construction. So if I was only considering this regular expression, only this one right here, I would make this the final state, make that the start state, and I would be done. So next, let's proceed. So now I need to make it so that it concatenates 0 on the front. So now we got to go through this process carefully. So which box do we need? So let's go over there. Which box are we going to need? So we're going to perform a concatenation between the regular expression for 0 and the current one we have on the rightmost side. So note, because of concatenation, I'm going to do them in order from back to front, but it doesn't matter. So which one are we going to use? The first one, the second one, or the third one? It's the second one, right? Because that's concatenation here. I deliberately didn't want to show all the operations, but we're going to use the second one. So remember, it is whatever the epsilon NFA for the first one, epsilon transition into the second one's start state. So what does that look like? Well, it look like this, right? So that's what R would be. So this would be the epsilon NFA for R. Then we have what? We have the epsilon transition to the start state of the other epsilon NFA. So this accounts for this so far. So far, that's what the epsilon NFA would look like. Note that if I was done here, again, this would be the final state. This would be the start state. Now we got to incorporate what I have right here. So do notice how this feels very much like a bottom-up construction, because it is. It can be viewed that way. So notice that I'm making bigger and bigger epsilon NFAs. So next, notice that I have actually already made this, so I can actually use that pattern to help me do this. So check this out. This is going to be a little bit weird at first. So I'm going to actually go over to that board because I'm just going to have a little bit of fun with this. So we have the bits and pieces, right? But now notice that this one has a star on it. So check this out. So I already know how to deal with 1 or 0, but now I just have to put star on it, right? So I'm just gonna make sure I got an idea where I'm at. So we already know how to do that part, right? So we already have the two disjoint, the two pathways with the epsilon moves like this, 1, 0, like that. We know how to do this. That's what we had before, right? For 1 or 0, like we have right there, this part. So now we got to put the star part. So we have to use the star construction that we had over there. So this is the fun one. So let's see, I need 2 new states. I have an epsilon move there, epsilon move here. Then I'm going to introduce an epsilon transition from the old final state to the old start state. And then I'm going to have an epsilon move from the new start state to this new final state for this particular part. So now we've incorporated, now we have this 1 or 0 star part. So that's it right there. Now, let's put it all together now. Now we got to concatenate what this would be with this. So check this out. So first, because I'm already at this stage, I'm going to, since I don't want to walk all the way over here again because I'm all silly like that, I'm going to make that the start state because that's going to indeed be the start state. Now, concatenation. That's the epsilon NFA for this. This is the epsilon NFA for this. I'm going to concatenate the result. Here we go. So it says that I'm supposed to put an epsilon transition from the old final state for this epsilon NFA, which is going to go over here. So I have an epsilon transition from that board to this board. And then I get over here. And this is supposed to be the final state, because that's the final state of this epsilon NFA. And there we go. So this is the resulting epsilon NFA for this regular expression applying Thompson's construction. Are there any questions? Any questions? Any questions at all? I had to do that for dramatic purposes. But yeah, what we're going to do is I wanted to just show you Thompson's construction. That way you could see how you can build an epsilon NFA. Now, because this isn't technically part of the proof, I'm going to give you a skeleton of how you would use something like this. So I haven't really cast Thompson's construction in a formal, I guess in an algorithmic way. I described it as a mathematical construction. So I'll let you think about how you might go about that process. But there's many ways to describe it that way. But as long as you understand this idea of building epsilon NFAs out of other epsilon NFAs, and this decomposition of the regular expression, so it's kind of like two big pieces here. One, breaking into the smaller pieces, and then, of course, building up the epsilon NFA. And there's many, I by no means am I going to be here and tell you that you would exactly do it that way, because there's so many ways you can better optimize this process if you have other parts of the epsilon NFAs already built. For example, if you already have one that you already constructed, there's no point in rebuilding the whole thing all over again if you already have a pre-existing part that you can reuse again, akin to our example over here. But the point I'm getting at is that this is the main idea of Thompson's construction. I've shown you how it works in this one part of the proof. But here's kind of the big idea. So you have a regular expression. Use Thompson's construction, or the algorithm, like it's when you actually carry out this process. So you take Thompson's construction and you end up with an epsilon NFA. This will actually recognize the same language as that describes. Then what you do is use the subset construction or any other variant that will turn it to the desired type of automaton. If you'd like. If you want to keep it as an NFA, you can keep it as an NFA and simulate that. But most certainly, if you want to turn it to a DFA, you can use subset construction. Then when you're at this stage, you might say, Dan, well, like, what can you do there? Now, weeks ago, I had talked about this idea of state minimization. So the epsilon NFA you might end up getting may have a bunch of redundant states in it. So you'll notice very quickly that there's like, okay, there's this epsilon move right here, then there's a 0, then there's another epsilon move. Perhaps I could contract some of these states that are redundant. And indeed, you can do things like this. Once you've got a DFA, you can construct a minimized DFA, which I haven't talked about how you do this, but it's a dynamic programming algorithm that exists that does this. you can minimize the number of states of the DFA. So if you're wondering a workflow for how you would go from a regular expression to something that you can get with a DFA, this is exactly what you can do. But yeah, no. So that's everything I have here to show you for today. But when I come back next time, I'll be either talking about another topic or I'll be talking about the other part of this proof. Namely, how do we go from a DFA to a regular expression? That's the piece we're missing in our proof. So, that being said, I don't see any questions. I think we're doing good on time here, and I think this is a great place for us to stop because the next part of the proof, I would argue, takes some real careful time to go through. So, whether we talk about a new topic next time or we're going to talk more about this, either way, we're going to have ourselves a blast with the other part. So, before we go, I want to say thank you so much for coming out and joining the fun. It was lovely getting some nice questions and participation about when we were playing around designing regular expressions. I appreciate it. This is one thing that makes the lectures much more interesting is when there's questions and there's a lot of interactivity. So even if you're not sure about the answer, please try to chime in. It's helpful because it's a part of the learning process. You know, when you make a mistake about something, don't feel bad about that while we're learning, because the thing is, it's a part of this process where we work together to figure out how you do it, or figure out the argument, because bouncing ideas back and forth, that's the core part of this academic discourse, is batting around ideas. So when we talk about that, whether we're designing regular expressions today or we're talking about some of this stuff, all those little steps, if there's anything that you're not sure about, ask about it or have some fun with it in the chat. Man, I gave some pretty good artillery to anybody that's doing text-to-speech here today. But anyways, later today I'll have the notes from today's lecture available on Patreon and Subscribestar. So you can check that out at patreon.com/pagewizard. You also see the links at the end in the closing for the stream here as well. So if you enjoyed this and you want to see more computer science educational content and more, later this week I will be playing some more Chrono Trigger here. Do subscribe, tell your friends, come join the fun, comment, tell people on social media, okay? I'm only one person, so please consider supporting academics outside of universities and all the hard work that I do here to try to make computer science more affordable for people to learn. So I want to say thank you so much and have yourself a beautiful day. I'll see you later. Bye-bye.